Okay, so let's take a few moments to talk about how to derive the maximum likelihood estimators for a logistic regression. Okay, so I've broken this down into 5 steps, starting with some notation. Then we'll find our likelihood function because we're finding the maximum likelihood estimator. So we'll find our likelihood function, and we'll find the log likelihood because the maximum of the log likelihood is going to be exactly the same as the maximum of the likelihood. It's a property of log. All right. And then we'll find the first derivative because we want to find the maximum. So one way you can find maximums is find where the first derivative equals 0. So then we'll set it equal to 0 and we'll try to solve. Now, if you we'll kind of get to a point where we'll notice that there is no closed form solution. Okay, so unfortunately we won't be able to solve this first derivative equal to 0, but from there you can kind of use a computer to be able to basically search and find where this first derivative equals 0, and then that's where the maximum likelihood estimators are. Okay, so let's start with the notation. All right, so let us assume that yi follows a Bernoulli distribution. Now, why Bernoulli? Bernoulli because Bernoulli is a distribution for zeros and ones. All right, so follows a Bernoulli distribution, and the probability that y equals 1, right, which is the parameter that a Bernoulli distribution takes, is going to be pi, and I'm going to take all of those independent variables xi. All right, so xi is going to be a vector, so to note that it is a vector, I give it this little hat, and it's 1, okay, 1i, 2i, and then say I have p independent variables, okay? And the reason why there's this 1, this first leading 1 is for an intercept, all right? I'm going to go ahead and define my coefficients, beta, right? These are what I want to estimate. Beta is beta naught, which is the intercept, beta 1, all the way through to beta p. All right, so y follows a Bernoulli distribution. The probability that y equals 1 is equal to this pi of xi. All right, and what is pi of xi? This equals 1 over 1 plus e to the power of, I'm writing exp to represent e to the power of negative xi transpose times beta. Okay, and this comes from the logic function, all right, which I think that is worthy of a video of itself. Okay, so I will include another video where I'm going to discuss this logic function. But basically, this you can find this relationship with the logic function, which is the probability that y equals 1 equals the log of the probability that y equals 1 divided by the probability that y equals 0. Okay, this is the logic function. And in logistic regression, the logic function, probability y equals 1, equals x transpose beta. Okay, so this is this linear term here that is equal to the logic function. All right, so if you were to rearrange this, you could find what we see here. And as I said, I can show that in another video, but kind of takes a little bit of time to build up between those two. But you could spend a few moments and try to rearrange this and show this relationship. Because remember, what is pi of xi? This is equal to the probability that y equals 1, right, by definition of the Bernoulli. Okay, so setting up notation still, so that I do not have to, I can kind of be a little bit lazy and I don't have to write exp negative x transpose xi transpose times beta so many times. Instead, I'm just going to call that new I, right? And that's just for convenience as I'm doing this derivation. All right, so now I have the probability that y equals 1, or pi of xi. This equals 1 over 1 plus nu I. All right. All right. So that's my notation. So this is number 1, all of my notation. Okay. So now let us do number 2, which is to find our likelihood function. All right. So likelihood function with regards to these coefficients, beta. All right. In general, that this is the, well, actually, let me skip ahead. In general, a likelihood function is the probability of basically all those different y's that you have. Okay, that's what a likelihood function is. All right, and since we're assuming that all of our y's are independent, right, we can say this is the probability, the product of all the probabilities. Okay, yi equals 1. Okay, so the product of all the different probabilities. Well, we have a Bernoulli distribution for the probability of y. Okay, so what is a Bernoulli? It's going to be this, the probability that y equals 1, which is this pi of xi, to the power of yi, 1 minus pi of xi, and then 1 minus yi, right? This is straight up what the Bernoulli distribution looks like, okay? A Bernoulli with parameter pi of xi. Okay, so instead of it just being p, now it's pi of xi. All right, okay, so we can do some simplification. So before moving on, let's go ahead and plug in what is pi of xi. Okay, it's the product from I equals 1 to n. All right, what is pi of xi? It is 1 over 1 plus nu I. Okay, 1 over 1 plus nu I. All right, so let's do some more simplification. All right. So let's simplify what we have over here. All right, so 1, right, if I want to simplify this, this is the 1 is the same thing as 1 plus nu I over 1 plus nu I. Right, why did I do that? Because I want the same denominator. So now I need to subtract this, okay? So the 1's will cancel, and I'll be left with nu I in the numerator, and then 1 plus nu I in the denominator. All right. All right, that's as simple as I'm going to get for the likelihood function. Okay, so beta is a vector, so that's why I have the little hat. All right, and remember beta is sitting inside these nu i's, right? Because what is nu I? There it is, it has that beta. Okay, so it's a little confusing because you don't see any betas over here, but they're inside that nu I. All right, so that's my likelihood function. So now I'm ready to find my log likelihood. Again, we do log likelihood because when I'm taking a derivative, it's a lot easier to find the derivative of a bunch of sums than the derivative of a product. And since the maximum of the log function is the same as the maximum of the function, you know, it's a nice property. It's helpful for us to use log likelihood when we're looking for a maximum likelihood estimator. Okay, so log likelihood. All right, so when you take the log of this, all of these, the products become a sum from I equals 1 to n. Okay, then I'm going to have the ln 1 plus nu I to the yi. Looks like I dropped my I there. All right, so then this is a product here. So that becomes a plus, right? The ln of nu I 1 plus nu I. All right, so now let's use some properties of log. Okay, so we can take this exponent and bring it down. All right, so I end up with the sum from I equals 1 to n of yi ln of 1 plus nu I plus 1 minus yi times the ln of nu I 1 plus nu I. Okay, so now I can do some more simplification, right? What is this? This is the same thing. So it's 1 over, so that's the same thing as to the negative 1 power. So now once again I can bring that down. And so I have the sum from I equals 1 to n of negative yi, the ln of 1 plus nu I, okay, plus 1 minus yi. All right, and then I can do a similar, so I have a division here. So this is the ln of nu I minus the ln of 1 plus nu I. Right, so I'm just kind of using some properties of log. Okay. We can still simplify this some more. Okay, I'm just rewriting that first part. Now over here I have basically two binomials, so I can just FOIL them, right? Multiply by the first and then multiply by the second. So what do I have? I have the ln of nu I minus the ln of 1 plus nu I. Then I have minus yi times the ln of nu I. Okay. Then I have plus yi, the ln of 1 plus nu I. Okay, so let's see if I have any cancellation, and I do. It looks like this guy cancels with that guy. All right, and I think that is the only cancellation that I have. All right, let me just double check. Yep, so then this equals the sum from I equals 1 to n, and what do I have? The ln of nu I minus the ln. Actually, let me take that y out. All right, so I have, let's see, yi nu I, okay, then minus the ln of 1 plus nu I. Okay, so I wanted to write these guys next to each other because they have like terms. Okay, so now I can actually simplify this a little bit more. And what do I have? I have 1 minus yi times the ln of nu I minus the ln of 1 plus nu I. Okay, great. So this is my log likelihood function, and I'm going to need to take the derivative here in a second. So let's go ahead and plug in for nu I. What is nu I? It's the ln of, here, let's scroll back up to look at what is nu I. E to the power of negative xi transpose times beta. Okay, so what is this? E to the negative x transpose times beta. Okay, so I just plugged in for nu I there. Minus, I'm going to run out of room, so I'm going to do this down here. Minus 1 plus e to the power of negative xi transpose times beta. All right. So let's see here. I have this guy will cancel with this guy, right? So I have this is equal to I equals 1 to n of 1 minus 1 minus yi, and then I have this multiplied by negative xi times beta, xi transpose times beta, should be transpose there. Okay, minus this ln of 1 plus e to the power of negative xi transpose times beta. Okay, so now I've run out of room on my screen, so I'm going to move this up. Okay, so this is the log likelihood function, right, which is the end of step 3. All right, so once we have the log likelihood function and we're trying to find the maximum likelihood estimators for beta, the next step will be to find the derivative with respect to beta. So let's go ahead and do that. What we want to do is find the derivative of the log likelihood function with respect to beta. Okay, so we have the sum from I equals 1 to n. Okay, and so now when I take the derivative of this first term here with respect to beta, basically I will have this piece here, right? I will have 1 minus yi times negative xi transpose. All right, I'm taking the derivative with respect to a vector. All right, so I'm taking the derivative with respect to this vector here. All right, now to find the derivative of this piece, I need to remember how do I find the derivative of a log, right? So that would be 1 over what's inside of the log. Okay, so this is going to be quite a bit of a chain rule here. Okay. And then I take the derivative of what's on the inside of the log, right, which would be this. The 1 would go away, but then I would have e to the power of negative xi transpose. Okay, so that's the derivative of the inside. Then I would need to take the derivative of the inside of the e to the exponential power, right? So this would be multiplied by, the inside of this would be just negative xi transpose. Okay, all right, good. So let's see here. I have a little bit of simplification that can happen. So I can pull that negative sign out. And I have 1 minus yi times xi transpose. Okay. Minus, plus, because the minus and the minus here make a plus. E to the power of negative xi transpose times beta. 1 plus e to the power of negative xi transposed times beta. All right, times xi transpose. Okay, so lastly, you could pull out, so we'd have negative 1 minus xi or yi, all right, plus e to the power of xi times beta, 1 plus e to the power of negative xi transpose, I forgot my transpose, times beta, right? Note that this piece here is a scalar, all right? And so then it gets multiplied by this vector here. So it's going to be a vector, this vector is the same size as beta. So that's why this, when I'm taking the derivative with regards to beta, I'm going to have a vector of answers, right? One derivative for each beta. Okay, so now in step 5, right, we would, in order to find the maximum, we would take the derivative and then we would set it equal to 0. Okay. 1 minus yi plus e to the power of negative xi. Okay, 1 plus. All right. Now I would need to solve. Okay, so now I would need to solve for beta. Okay, so if you try to solve this for beta, you will get to a point where you'll realize that there is no closed form solution. So this is why what we'll do is we'll use our data, our different yi's, right, and our different xi's, put in our data, and then we'll use a computer algorithm to basically find where this equals 0 for different values of beta. Okay, and of course you should also show that this equation is for a maximum and not a minimum. And how do you do that? You would need to find the second derivative with regards to beta. Okay, so I'll leave that for right now as a separate exercise, something else to go through. But it can be shown that this function this is going to find the maximum, not the minimum. So once again, you'd have to find that second derivative to show that. All right. Thanks for watching.